So we're going to start off with, well, what is a vector? By 2. So what is a vector? What is a vector? Right. What's a vector? Can somebody tell me what a vector is? What is a vector? Yeah, Flo.
It's a line with both magnitude and direction.
Okay, so it's something with magnitude and direction. So a construct, say, with both magnitude and direction, right? And it's usually represented by some line segment, right? Usually represented as a line segment between 2 points, say some point A and some point B, and you have a line segment. So usually represented by a line segment. Right? That line segment captures the notion of magnitude, and to some degree it captures the notion of direction, right? But if it's just a line segment, you don't know if it's pointing this way or if it's pointing that way, right? So in general, you put an arrow on it to indicate that it is going in this direction, right? Because you want some direction, and you don't want to say it's either this direction or in the opposite direction, right? So you need to specify, right? So right. So I think the way we define it, at least for now, is a vector is a directed line segment between 2 points. 2 points A and B, and we usually denote A, B with an arrow above it. Okay. If it's going from A to B, then we write it as AB with the arrow going from left to right. Okay. And just terminology, this thing is called the initial point. Initial point, this thing is called the terminal point. Initial point and terminal point. Okay, so that's just language. Not much in the way of ideas. Okay. When are two vectors equal to each other? Well, we've got these things. We want to say that we want to have some way of talking about them. Are they the same? The most simple question is, are these vectors the same vector, right? So how do we define equality, basically? And this is so equality, and this is sort of a geometric definition. We say, well, maybe, when are two vectors equal to each other? Peter?
When the magnitude and direction are the same.
When the magnitude and direction are the same. Yeah, they basically, a vector is magnitude and direction. If their magnitude is the same and the direction is the same, then they're equal to each other. So more pictorially, we say that if you have one vector and another vector, and you can slide them over. This is very not a very good definition, but this is what we're going to say. If you can slide it over and they're equal to each other, it's the same. So if they are translates of each other, if vectors u and v are translates of each other, we say that they are equal to each other. Okay, so all these guys are the same, are supposed to be the same vector. Okay. As long as you can slide them over and they are exactly the same. Okay. Okay, so the point is that position doesn't matter. And so for convenience, since it doesn't matter where the position is, one takes the origin as the initial point. Right. So we're just going to assume that every vector is going to start at the origin. So, I mean, and that guy will represent, all the other guys who aren't at the origin. Okay, so just for convenience, we'll take the origin as the initial point. Then the vector is determined by its terminal point. Right? Because you already know what the initial point is. Okay. And so this leads us to the so-called component notation. If I write bracket xyz, this denotes the vector from the origin 0, 0, 0 to the point xyz. Probably you've seen this with me before. And these guys are called, the x, the y, and the z are called the components of the vector. Okay, so this is just how we describe vectors, right? Vectors for us are going to be these determined by the terminal points, and in some sense we'll conflate the point and the vector. Sometimes we'll be talking about a point, and we'll also talk about it as if it were a vector, the vector going from the origin to that point. So one tends to be sort of sloppy. Okay. Okay. So from the point of view of component notation, we can talk about magnitude and direction. There's a way of describing magnitude and direction. So what are magnitude and direction in terms of component notation? In terms of components, right? If you have a vector, suppose you have a vector xyz. Okay, you have some vector xyz. The magnitude of v, denoted with a double absolute value sign, okay, is defined to be, you probably know what it is. What is it? If the vector has components x, y, and z, what's the magnitude of it? What's the length of it? Does anyone know? It's okay if you don't. Should I pick somebody around?
Yeah, the square root of x squared plus y squared plus z squared.
The square root of x squared plus y squared plus z squared. The magnitude of v is defined as this. You may have seen this before. If you have a colon and an equal sign, it means this thing is defined to be that thing. It's defined to be this. And this is a reasonable definition. Why is this a reasonable definition? Why does this make sense? What is this thing, x squared plus y squared plus z squared?
Distance.
It's the distance. The distance to what? To the origin, right? So, right, you've got this point in space, right? This is the distance to the origin of that point. In other words, the length of the vector, the magnitude of the vector, right? So that's why we define this as the magnitude. Okay, let me just make one observation. let's say again that V is x, y, z. Right? The magnitude of the vector is going to be bigger than or equal to the size of each component, the magnitude of each component. Right? It's bigger than if suppose I'm going to draw this in 2 dimensions, but it works just as well in 3. Right? Here you have this point x, y. This length here is the magnitude. Right? This length here is the magnitude. And you see that, right, this length here is the absolute value of x. This length here is the absolute value of y. Absolute value of y. Right? And the magnitude is bigger than each of those guys. Right? The magnitude dominates the size of each component. Right? So it's bigger than the absolute value of x, it's bigger than the absolute value of y, and it's bigger than the absolute value of z. It's bigger than all of those things, so it's bigger than the greatest of them. So I'm just going to make an observation that may prove useful later on. Does that make sense to people? Right? The magnitude, the length, this length is going to be longer than any of the other lengths. And you can see that geometrically, or you can see that from the distance formula. Right? Look at it. You look at the distance formula. Well, the magnitude is going to be x squared plus y squared plus z squared to the half. Right? And you say, well, this thing is definitely bigger than or equal to x squared to the half. Right? Because if I throw things out, it's just going to get smaller. Right? So that's true. And what's this? This is the absolute value. Right? This is the absolute value. And we could do the same thing. Same for absolute value y and absolute value z. Right? So you could make this observation either algebraically, or you can make this observation geometrically. Everyone all right? Okay, good. Nothing fancy so far. So, okay. So, for us, the vectors are basically a replacement for the number system, right? For vectors, we want to we also want to have some sort of vector arithmetic or vector algebra. So like, how do you add vectors? How do you multiply vectors? Can you multiply vectors? Can you divide vectors? No, maybe not. Okay, so for us, vectors are some sort of generalized numbers. So we're going to want some way of adding them and some way of multiplying them. Okay. So let me give the definition. Let's say that we have vector 1, which is, let's say, u1, u2, u3. And we have vector 2, which is v1, v2, v3. Okay. So these things are the components, right? So if you want to make it concrete, just pretend that u is 1, 2, 3, say, and v is 4, 5, 6. Right? If we don't, that's all we said. Suppose you have 2 vectors, and here are the components. Okay. We define. We want to have some way of adding vectors. We want to have some way of adding vectors. How does one add vectors? If you have one vector, u1, u2, u3, another vector, v1, v2, v3, how do you add them? Is anyone familiar with this?
Add u1 and v1 and
you add it component-wise. You say, we're going to define it to be the vector you get by just adding each component. the sum vector is going to be the vector whose components are the sum of the components of the original vectors. Okay. And for lambda a real number, we define lambda times u as, so we have a way of, we're going to define a way of taking a number and multiplying the vector by that number. Does anyone know the definition of this thing? You have some vector, u1, u2, u3, and you have some number. Anyone familiar with this? Ito.
Just multiply lambda with each component.
Yeah, you just multiply every component by lambda. Okay, so concretely, right, here, if I say u plus v, then u plus v is going to be 5, 7, 9. And if I had something like negative 3u, that would be negative 3, negative 6, negative 9. Right? So one adds vectors by adding them component-wise. One multiplies this vector by a scalar by scaling each component, scaling every component. Okay. Any questions? Okay. So right. So pictorially, if you have, say, so I'm going to do this in R2, U1 and U2 here, and you have V1 and V2, right? V1 and V2, then the sum, by the sum, you're going to take the x component of this guy and the x component of this guy, and you're going to add it together, right? You get U1 plus V1, and you take the y component of this guy and the y component of that guy, and you add it together, right? So you get U2 plus V2, you get U2 plus E2, right? And so you would end up with this guy here. This thing is the sum, U plus V. This is U, and this is V, but this thing here is U plus V, right? And as you probably know, this amounts to just taking one vector and putting it at the end of the other, and then creating this new vector. This terminal, using this thing as a terminal point, gives you the sum vector. So adding vectors amounts to just lining them up head to tail, and then creating a new vector. And then scaling vectors, if I have a vector u1, u2, and I multiply it by some number, what does that amount to do?
It means like adding it to itself so many times.
Mm-hmm. So if I say twice this, well, then you're going to multiply each thing by 2, right? And so you get the double vector. Right? You stretch it, you scale it, right? That's why we usually call, in vector calculus, one often calls these things scalars, because they're used to scale. Number and scalar mean the same thing, okay, in this class. Okay, so it just means, so scaling, so this is called, so this first thing is called vector addition. Vector addition. And the second thing is called scalar multiplication. Right? It's not vector multiplication. You're not multiplying a vector by a vector. You're multiplying a vector by a scalar. Okay? And that's a little bit unsatisfactory, right? Because if these were numbers, you multiply numbers by numbers. But here we're not multiplying vectors by vectors. We're multiplying vectors by scalars. Okay. And if we multiplied this by a negative number, it would just change the direction. It would flip it, and make it go in the opposite direction. Okay. Okay. So we have vectors, and we have some. We're starting to have some way of adding and subtracting and multiplying them. What should correspond to 0? What is 0 in this case?
Origin.
The origin? Okay. Why is that good? That's good, actually. The origin is a good thing. So the origin is this thing 0, 0, 0. Okay? And you notice that if you add this guy onto anybody, then nothing happens. Right? If you add the origin onto, if you add the 0 vector onto any vector, then nothing happens. And that's what you would hope, right? Because with numbers, you have a 0, the number is 0, right? And you add the number 0 onto anything, and nothing happens, right? So this is what's called the additive identity. Additive identity. Something that when you add, nothing happens. Okay, and then so for vectors, you also have an additive identity. It's the 0 vector. It's a 0 vector. When you add onto it, when you add this thing onto things, then nothing happens. Okay. So you notice that it doesn't. You can't multiply by the 0, right? You can't multiply, but you can multiply by 0 the number, but you can't multiply by 0 the vector. So it's not quite as simple as the number system. Okay. So just some basic laws. Basic laws of vector algebra. And these are just like they are for numbers. If you look at u plus v, what am I going to write on the other side? U plus v is equal to what?
V plus U.
V plus u, thank you. I know it's not that great. Okay, not that great question. So u plus v is v plus u. Like there's a commutative, addition is commutative, right? So you have a commutative law. Right? And you think, well, do we really have a commutative law? Is that true? Does the commutative law hold? Well, let's see. Over here we would have, on the left we would have u1 plus v1, comma u2 plus v2. I'm only going to write it in 2 dimensions, just to save chalk. On the right you would have v1 plus u1, v2 plus u2. Right? And are those the same? Yes, they are the same because numerical addition is commutative. Right? If you add numbers, you can change the order. Right? So these v plus u1 plus v1 is the same thing as v1 plus u1. Right? So the commutativity of vector addition follows from the commutativity of scalar addition. It's a consequence. Okay. Similarly, you know what I'm going to write next. It doesn't matter the order in which you add vectors. Right? You can add the first 2 guys first, or you can add the second 2 guys first. Right? You have an associative property. Third, there is a 0. There is an additive identity. So there is an additive identity. Fourth, there are additive inverses. So there exist additive inverses. Right? There is, if given any vector, there's some other vector you can add to it to get back to 0. To get back to the additive identity. Right? That the additive inverse is going to be just negative for your original guy. On the other side, one has this sort of thing. 0, the number 0 times any vector gives you the vector 0. There's a multiplicative identity. Right? There's a number that you can multiply by, and it does nothing. And it is again the number 1. Again, things that are familiar. You have sort of an associative law of multiplication, right? You can multiply by the second scalar first, or you can multiply the two scalars together. It's basically everything behaves as you think it ought to behave, right? It's nothing, there's nothing surprising here. Right? Right. You have a distributed law, and you have another distributed law. Right? You have two kinds of distributed law. Here you're using vector addition, here you're using scalar addition. In any case, the moral is everything is as you expect it to be. Okay, so there's nothing particularly surprising about this. About when you're doing vectors, basically you can say, oh, it's going to work out as just like it would for numbers. The only thing that's different is that the multiplication is not of vectors, right? You don't have this. If I make this doesn't make any sense. Right? If I write this, nonsense. Right. Okay. Okay. Everyone all right? We actually haven't done very much, right? It's not, we haven't done anything particularly exciting. So if you're bored, then that shows you have good taste. I used to present all of the math as if it were exciting, but in fact that's not true. Right? Some of it is not exciting. Okay, so let's look a little bit at the interaction of magnitude with algebraic operations. So two observations. So here's observation number one. If you have some number and you have some vector, let's say in R3, it doesn't matter. So are you familiar with this? When I write R3, is everyone okay? R3 just means space, right? It means that our vector looks like it has 3 components. So if you have something like that, then the magnitude of the scaled vector is what? What am I going to write? The magnitude of, if you take a vector and then scale it, then what happens to the magnitude?
Each component is multiplied by the scalar.
Each component is multiplied by the scalar. So in the end, what's going to happen? You can work it out. You say, well, okay, so I'm then going to get the, each component is going to get multiplied. So I'm going to magnitude of V, I'm going to V1 squared, V2 squared plus V3 squared and a half, right? So here's my scratch work. I'm going to secretly work it out beforehand, right? And then what happens? Think about it for half a minute. Tell me what the answer is. Okay, I'll go walk around. What's the answer? I'm sorry, I forgot yours.
Sydney?
Sydney, yes.
Wait, wouldn't it just be the magnitude times lambda?
Close. There's one small correction. Melissa?
Well, it's going to be the square root of lambda times what it was before. Like in square root. Okay, like if
You're
you
close.
had
You're also close.
the square root of 14 before and your scalar was 2, then now you're going to have the square root of 28. Does that
Yes.
make sense?
Yes. Okay. So so what? So do I just get? Is it just lambda times the magnitude? Is that
No,
what I
because
get?
there's a square root.
So is it the square root of lambda? If you scale it, then the
Lambda
magnitude
squared
is magnitude.
to the square root?
Lambda squared, square rooted. That's probably the closest. That actually is the right answer.
Okay.
Lambda squared, square root. But you know what that is? What's a square root? You take a number, you square it, you take its square root. What is that? That's the absolute value, right? So you get the absolute value of lambda times the magnitude, right? And that makes sense because the magnitude should be a positive number, right? Magnitude should be a positive number. If I multiply by a negative number, if I scale by a negative number, still the magnitude will be multiplied by a positive number. Right? If I multiply, if I have a vector and I say, what's the length of -3 times it? Well, that will be 3 times the magnitude of the original vector. It's not going to be -3. Like magnitude is positive. And you could work that out from here, you know, just by reducing, just by simplifying this expression. Okay, so that's our first observation. The second one, it's a little bit vague, so I'm gonna just this. The magnitude of u plus v is less than or equal to what? This one is pretty vague. So if you less than or equal to
Either
u?
by itself.
U by itself? Let's think about that. If I have one vector, and I have another vector, and I look at the third vector, if I look at the sum vector, I'm saying that the size of the sum vector is going to be smaller than, will it be smaller than this? No. This is pretty vague, so if anyone figures it out, I'll be lucky. You have a triangle. What we're saying is that the length of one side is going to be dominated by the length of another side. Oh no, but
Would it just be u plus v?
yeah,
Okay.
then the sum of the lengths of the other sides, right? So if you have any triangle, the length of one side is smaller than the sum of the lengths of the other side, right? Because this is the shortest distance between those 2 points, right? If you go any other route, then you've made it longer, right? So this is a statement called the triangle inequality. Triangle inequality. And it's written like this, that the size of a sum is dominated by the sum of the sizes. The magnitude of a sum is dominated by the sum of the magnitudes. And in the field of math that I work in, one uses the triangle inequality all the time, like every day. It's like your basic tool, like using a hammer or something like that. Although there are some people who hate it, who hate the triangle inequality. I have one friend who says that this is the fact in mathematics that he hates the most. Because in mathematics, one often tries to understand exactly what things are. And if you're using, to him, this is his way of thinking. If you're using the triangle inequality, you've given up already. Right? You're not thinking about this. You're saying, I'm going to think about something a little bit sloppier. Right? So that's why it means it. Okay. Okay. So a couple more ideas. These are all. These are just sort of facts that will come in handy to you. We initially when we talk about vectors, we say, oh, they're things with magnitude and direction, right? And we have some geometric way of talking about that. And then you recall we introduced the component notation, and we said, well, what's the component notation in terms of, what's the magnitude in terms of component notation? Okay, and then we talk a little bit about that. And now we're going to talk about what's direction. So, right, how do you express direction in terms of the component vectors? So, direction in terms of the component notation, excuse me. So, here's the definition. If the magnitude of a vector is 1, we call U a direction vector, or a unit vector. Either one. Okay. So so here's the picture. You have some vector v, okay, and then the vector in the same along the same direction with a magnitude of 1, we call this thing the direction of v. Okay, the guy who is in the same direction, in the sort of intuitive sense, with magnitude 1. So the unit vector with the same direction is called the direction of that vector. Okay. So this is what we mean by direction. These unit vector guys are what we call directions. Okay. So the question is, given a vector v, how does one find its direction vector? How do you find its direction vector? Right? Somebody gives you a vector v, right? So for example, v is 4, 5, 6. As it was before. What's v's direction vector? How would you find a unit vector that goes in the same way but has length 1? You can do it. How would you do it? You would like a new vector, but it has to be length 1. And it's going to be in the same direction. Right? Well, how do you get a vector in the same direction but of different length? Scalar. Right? So we got to multiply it by something. What should we multiply by?
1 over the magnitude.
1 over the magnitude. Great. Right? 1 over the magnitude. Right? So you just take the unit vector in the same direction as v is just v divided by magnitude of v. Right? Or maybe I should write it more like this: 1 over the magnitude of v times v. Right? Lambda v, where lambda is 1 over the magnitude. Usually people write this as v over magnitude of v. Okay. So in this case, right, the magnitude of v is the square root of 16 plus 25 is 36. So that's 4177. Right. So here the direction vector is going to be 4 over 77 divided by So this is also called the normalization of V. Okay. Magnitude is often called norm. Magnitude and norm are basically the same thing. Norm and magnitude. So normalization, you're dividing by the norm, and you get a vector of norm 1. You get a vector of length 1. That thing is called the normalization. Okay. Okay, so at this point we make sort of a funny observation that in that case, a vector V really is magnitude and direction, in the sense that if you take any vector, you could write it like this. You could take any vector, any non-zero vector could be written as this number times this vector. Right? And this number is the magnitude, and this number is its direction. Right? So a vector really is magnitude times direction, in a very literal sense. You know, at the beginning we said, oh, a vector is something with magnitude and direction. Right? In this sense, really a vector literally is magnitude times direction. So, okay, a couple more simple statements, simple ideas. We say U is parallel to V, so U is parallel to V if the direction of U equals the direction of V, or the direction of U equals minus the direction of V. So I'm going to just put it together. Direction of U is plus or minus the direction of V. If they're in the same direction or they're pointing in opposite directions, then we say that they're parallel to each other. Remark, we say that the zero vector is parallel to everybody, to all vectors. And I'm just going to make an observation and let you think about it. Vectors are parallel if and only if one is a scalar multiple of another. One is a scalar multiple of the other. So this symbol means is if and only if and only if and only if. So they're parallel if one is a multiple of the other, and if one is a multiple of the other, then they're parallel to each other. The logical implication goes both ways. And to end with just the final non-interesting fact, one notates the last uninteresting fact. I'll be honest. One often uses this notation I, J, and K to denote the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so these are the, what are called the basis vectors. These guys are called the canonical basis vectors, canonical basis, or the standard basis vectors. In R3. Okay, and the point for these guys, the point is that every vector can be expressed as a combination of these vectors. There's actually a point to this point. Any vector can be expressed as a combination of these three in a trivial way. Right? Like if I have 4, 5, 6 again, that could be expressed as 4i plus 5j plus 6k. Anybody can be expressed in terms of these guys. Okay. Oh, okay. So yeah, you should leave this room sort of shrugging at this point, but it'll get better. So that's it for today. Please turn in your whatever your diagnostic and your assumption is.